Boom! Yes, folks, Hume here again, all again. In this video, we're going to continue the discussion from the last video, which would have been Factorization 4, where we spoke about factorization of a quadratic expression. All right? So a brief recap up to this point in the series on factorization. Factorization 1, univariate binomial. Factorization 2, the bivariate binomial. Factorization 3, factorization by grouping. Factorization 4, factorization of a quadratic expression. And in this video, let me call it factorization 4b, if we want to use that notation, right? This is still discussing factorization of a quadratic expression, but with a couple special conditions imposed on the situation, right? So a brief recap of what we did so far. Well, what we did in the last video, that is. Somewhere at the beginning of the last video, we discussed the general quadratic ax squared plus bx plus c. And we said that for this term to be a quadratic, a, b, and c could have any value. We also said that b could be equal to 0, that c could also be equal to 0. We also said that a cannot be equal to 0 because a being the coefficient of x squared, remember this is the term that actually defines the entire expression as a quadratic. So this term in x squared cannot be equal to 0. A could be equal to 1, in which case you just have x squared. A could be less than 1, the a could be negative. There are a whole host of mathematical possibilities for the value of a. What a cannot be is 0, because as soon as a becomes equal to 0, this term disappears and leaves us with just bx plus c, right? Which is not a proper quadratic, right? That is actually a linear expression, right? Bx plus c is a linear expression. For those of us who recall the general equation of a straight line, y is equal to mx plus c, right? Y is equal to mx plus c. The mx plus c is the same thing as bx plus c. We just use m here and b here. So in other words, if bx plus c is linear, that is essentially the equation of a straight line. B is your gradient, for those of us who have some familiarity with straight lines. And c here is your y-intercept, right? So I'm bringing everything together so you see that it makes sense. Even when we change the letter in, the concept remains unchanged. All right? So bx plus c is a linear expression. So your a cannot be 0. If that happens, then you have a linear expression. So for this to be a quadratic, your a must be in the picture. However, your b could be equal to 0. If your b is equal to 0, we are left with, make sure this thing dry properly. We are left, if b is equal to 0, we are left with ax squared plus c, which is in fact a proper quadratic. Yeah? No problem. If c is equal to 0, we are left with ax squared plus bx, which is also a proper quadratic because the ax squared term is there. And if if b and c are both equal to 0 together at the same time, simultaneously, then we are left simply with ax squared, which is also a proper quadratic. Right? So the quadratic expression could also appear in one of these three forms here. right? ax squared plus c, where b is equal to 0, ax squared plus bx, where c is equal to 0, and just plain ax squared, where b and c is equal to 0. So I am going to preface the remainder of the discussion in this video by saying something, and I want you to take careful note of what I'm saying, because 99 times out of 100, and I will go as far as saying 999 times out of 1,000, anytime a quadratic appears in one of these three forms, we do not use the AC method to factorize, where factorization is possible. Let me say that again. Anytime you have a quadratic, remember a general quadratic is ax squared plus bx plus c. If you have a situation where b is equal to 0, right? If b is equal to 0, here a is equal to 0. That's not a quadratic. If b is equal to 0, or we have a situation where your c is equal to 0, or you have a situation where b is equal to c is equal to 0. In either one of these three cases, we do not use the AC method. Let me say that again. Anytime you have a quadratic that looks like this, or it looks like this, or it looks like this, we do not use the AC method. The AC method is used when you have a quadratic with all three terms in the picture. You have a value for A, you have a value for B, and you have a value for C. Right? This we could treat as a univariate binomial. This we could also treat as a univariate binomial. This is just a univariate monomial, which is one term. Right? So I'll do some examples now. Right? I will make the point by using the AC method on three examples like this. So in other words, I'm going to do it to show that you shouldn't do it, right? And I'm going to do that by actually letting b and c be equal to 0 in each one of these three situations. Hey, b equals 0, c equals 0, b and c is equal to 0. And I will go through it just to make the point that you don't need to do it. And the reason why I'm actually having this discussion is because one of my students earlier this year actually tried that. We were doing some factorization in class, and I gave them one, I think it was one like this. And she went down the road, and I was like, woo! A equals something, B equals something, C equals 0, ding, 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 ding. And that was a light bulb moment for me, because in all my years of doing maths, first as a student, and then teaching maths, the idea of using the AC method for one of these three had never occurred to me, and I had never even seen it attempted by other students. But boom, after all these years, here is one of my students trying this thing. And it was a genuine attempt, because she had just finished doing a whole exercise with a whole set of quadratics. Right? I give them some questions to do. So I guess seeing this and recognizing it as a quadratic, the impulse, the instinct at that point would have been just to continue with the pattern that you would have been practicing all the time. And that is something that we normally do. A lot of us find ourselves doing it at some point in some field, some endeavor. We have one pattern in response to a particular situation, and then the situation changes a little bit. Sometimes the change is a change that we mightn't perceive, or we might see the change and we say, nah, we could still do what we are accustomed doing. And you do what you are accustomed doing for situation A, when A is now situation B. You try that on situation B and you realize, okay, nah, we have a problem here. So this is one of those cases where, having been doing some exercises on quadratics, let me say you just went through 40 questions on factorizing quadratic expression. right? Or 30 or 20 or 10 or 50 or 60, 70 or 80, however many. And you see one of these, there are students who would try to do the same thing, especially seeing that we have discussed in my previous video the whole existence of the concept that B could be equal to 0 or C could be equal to 0. And that is something that's a lot of teachers don't really state explicitly. A lot of students will have to discover that accidentally on their own, or maybe with some other teacher apart from the teacher that they're working with in school or whatever. So here we are. We're going to consider the case where B and C is equal to 0 separately and together. So let us say, for example, that we have a quadratic where B and C are 0 together. So let me say that we have a quadratic. Now, we're going to have some fun here. Right? We're going to have some fun here. And again, I will keep saying it. Do not factorize using the AC method if B and C or B or C is equal to 0. Because watch the madness we're going to do here now. Suppose we have a quadratic expression. Now, let me try this properly. Hold on. Suppose we have a quadratic expression, and I'm using everything in x for now because I want it to line up with the general quadratic ax squared plus bx plus c. Let me say we have a quadratic 5x squared. Your b is equal to 0 and your c is equal to 0. Yeah? So you say, all right, a is equal to 5, b is equal to 0, and c is equal to 0. So we're following the same pattern that we established in the last video. You say, well, all right, AC is equal to 5 by 0, which is equal to 0. So far, so good, right? Except that 0, and this is something that I wanted to bear in mind if you never heard it before. Put it in your back pocket because it might come up again at some point. 0 in the strictest mathematical sense is not an actual number. 0 is not a real number, right? If we want to talk about the classification of numbers, 0 is not a real number. We cannot even class it as an imaginary number. It's just not real. 0 exists in a special bubble by itself. In any discussion of math at any level, you'll realize that the number is 0. Very, very special. In the strictest sense, it is not a number. It is more so a concept, an idea. And the idea or concept being that of nothing, nothingness. So we use 0 to represent nothing. Right? Nothing. Try to imagine that. Right? Nice. However, for the sake of this particular discussion, we will treat 0 as a number and we will apply certain numerical properties to 0. But just bear in mind that mathematically speaking, this is not proper mathematics. I just going a little outside now, just to show you the thing from a different angle, stimulate the thinking a little bit, so that when I tell you factorize 5x squared, you know with a certain level of conviction that we're not even trying to use the AC method here. And we have a couple other examples to come. Alright? So let me say that we're looking for two factors of 0 that will add together to give you, guess what? 0. Because we could remember we could write over 5x squared as 5x squared plus 0x plus 0, right? No problem. So 0 is equal to 0 by 0. Remember, in the regular factorization in the last video, we start from 1. See? Because 1 is a real number. 0 is not a real number. So we're bending the rules a little bit here just to make a particular point. Right? So 0 is equal to 0 by 0. So we write this over as 5x squared. Now 0 plus 0 is also 0. Right? So 5x squared plus 0x plus 0x plus 0. You see how much fun we have it? So this will be what? You take out x, you factorize. Imagine that we factorize it with 0. Papa, yo, what madness we doing? But let me do it now. Let me do it now. The madness. Method to the madness, right? So you factorize. You have x into 5x plus 0. And remember we had said in the last video, we ain't really sure what to do here. And yeah, we ain't really sure what to do. So here what we do. We start by putting the same 5x plus 0 here, because that's the only way we could proceed with the factorization, right? And what multiplied by 5x plus 0 will give you 0x plus 0. Well, guess what? 0? Yeah. 0 by 5x is 0x. 0 by 0 is 0. Again, remember, this is not proper maths, but I'm just flowing with it, right? So 5x plus 0 is the common factor, right? Into x plus 0. Papa, yo mama. Right? 5x plus 0 is 5x. And x is just x. Right? So you have 5x multiplied by x here. Right? Which we could have just gotten in one line, you know. If we had 5x squared, we can just say that is x into 5x. Right? All of that to drive home the point that if you're ever in a situation where you had to factorize 5x or 29x or 5x squared, sorry, or 29x squared or 6y squared or minus 17k squared, whatever it is, don't even think of doing this. This is nice to stimulate our discussion, but we don't do arithmetic with 0. We don't really do arithmetic with 0. There are certain situations where you use 0 in certain kinds of situations. But even in those situations, you're not really doing arithmetic with 0. You're just invoking the concept to take it from point A to point B so you could continue with the rest of the arithmetic. Right? So don't even think about doing this. The factorization of 5x squared is simply x into 5x or 5x into x. Same difference. Same commutative property that we discussed in the last video. Right, so that's example 1. That is the example where B and C were both equal to 0 at the same time. Let me take another example. Right? Let us say that C is equal to 0. No problem. C is equal to 0. Well, let me do an example now. What let's say there? Yeah? Let me do an example. C is equal to 0. Example being, let us say we had to factorize 4x squared minus 16x. Now, this is a univariate binomial. So this would fall within the category of expressions that we discussed in the very first video. But up to that point, maybe you didn't know that this was a quadratic. So you just factorize it as normal. Right? But now that you know it's a quadratic, now you want to complexicate the thing. You want to go A and B and C and thing, right? You know about quadratics, so you want to go right? Let me do it the normal way first. If I had to factorize 4x squared minus 16x as a regular factorization of a univariate binomial, I would just get 4x into x minus 4. Right? Straightforward and quick. But you know how things could be in life sometimes. Sometimes they get a little knowledge and a little extra knowledge suddenly complicate the thing. I have plenty instances like that in real life. You're doing something all the time. Nice, easy, and straightforward. And then as soon as they get a little knowledge, suddenly they start to go all over the place. And they want to try all kind of new fancy tricks. Now, this is a situation like that. You're factorizing this normally. 4x squared minus 16x, 4x into x minus 4. Boom! Now you learn about quadratics, A, B, and C. So check what you're going to do now. You say, well, all right, this is a quadratic. So A is equal to 4, B is equal to minus 16, and C is equal to 0. Okay, well, let me try that and see. So your AC is equal to 4 by 0, which is equal to 0. Watch it again. And again, we're treating 0 as a regular numeral, which it most certainly is not, right? So if we want two factors of 0, that will add to give you a minus 16. So in other words, two factors that multiply to give you 0, that add to give you minus 16, those are the add-ends. We discussed that earlier on, right? We want factors here, which will be add-ends to give you this. The only pair of values that will do that would be 0 multiplied by minus 16. Remembering, of course, that in irregular factorization, we start with 1. Excuse, this is not regular. This is not to be attempted in any exam, right? But we're just having the discussion, right? So let me take 0 by minus 16 as two factors of 0, sorry, that are add-ends of minus 16. So here what we're going to do. We say 4x squared plus 0x minus 16x plus 0, right? Because your C is equal to 0. We say we say x into 4x yeah, we say x into 4x plus 0. Now we ain't really sure what to do here. So here what we do? We say 4x plus 0 inside the brackets. What by 4x will give you minus 16x? Minus 4. Minus 4 by 0 will also give you 0. So x into 4x plus 0 minus 4 into 4x plus 0, which would give you 4x plus 0 as the common factor into x minus 4, which, as you could see, is the same 4x into x minus 4. Yeah? Look at there, one line. If we do it in reverse as we did in the last video when we were discussing factorization, we would have, let me say, 4x squared minus 16x plus 0x plus 0, which is the same 4x squared minus 16x, right? So we could say, well, the 0x plus 0 would disappear, but let us, for the sake of being absolutely facetious, treat this 0 and this 0 as if it actually had some kind of meaning, right? So we say here what? 4x into x minus 4, and then if we put the x minus 4 here, sorry, x minus 4 here, for the factorization that makes sense, factorization by groups, we say that this would be what? 0 plus 0 into x minus 4. So you say x minus 4 as the common factor into 4x plus 0. Pressure! Look at it. 4x plus 0 by x minus 4. X minus 4 into 4x plus 0, right? Which would then give you x minus 4 into 4x, which is the same thing we have here, right? All of this to reiterate that if you have a quadratic where c is equal to 0, do not try to impose the AC method on that. If c is equal to 0, what you basically have is something looking like this. You just factorize it as a univariate binomial. You take out the common factor of 4x into x minus 4. Braps. No problem. Right? Again, don't even think about doing this. Don't write this down anywhere to give to anybody, except if you're just having a facetious mathematical discussion as we are having right now. That has no place in an actual exam. Right? But we're going out, so we're thinking outside the box a little bit. Right, so let us do another example now, this time where b is equal to 0, and you will see here now is where the things start to get nice, real nice. Stay tuned and you'll see how nice it's gonna get. Right? So if b is equal to 0, what do we have? Right? We have watch the magic, watch the magic. It's sweet, you know, it's sweet. Right? Check it out. Let us say we have 2x squared plus 50. Papa, yo mama. Pressure any can, boy. Well, listen. If we had to factorize 2x squared plus 50. Again, univariate binomial, you could do that in one line and get 2 into x squared plus 25. No problem. Let us, however, for the sake of argument, see that I'm doing my quadratics now and I'm feeling good. So I recognize this as a quadratic, and I'm still not aware of how unwieldy 0 could be in mathematics. Try doing serious arithmetic with 0 on a calculator. Anything other than addition and multiplication, you will get an error if you try to use 0 in most instances. Right? So let me use the A and the B and the C now, the AC method, right? Quadratic. So B is equal to 0. So watch me. A is equal to 2, B is equal to 0, and C is equal to 50. No problem. So AC is equal to 2 by 50, which is equal to 100. Papa, yo mama, look trouble. Look trouble. Because we want 2 factors of 100 that will add to give us 0. What's the problem there? The problem is that because this is positive, we only have 2 variations where the factors are concerned. So you have positive multiplied by a positive, or a negative multiplied by a negative. We discussed that. The initial factors and the mirror. 2 by 50. 2 by 50, or minus 2 by minus 50. You could even go as far as saying 10 by 10 or minus 10 by minus 10. 20 by 5, well, that would be the same as 5 by 20. So once we get to 1, 2, 5, 6 wouldn't work, 7 wouldn't work. 4 would work, 4 by 25, minus 4 by minus 25. 5 by 20, minus 5 by minus 20, 6, 7, 8, 9, 10. 10. 10 by 10 minus 10 by minus 10. There is no way among all these factors here we could combine any one of these pairs to give you 0 here. Right? Because 2 and 50 is 52. Minus 2 plus minus 50 is minus 52. If you try 10, 10 and 10, kind of alright. But 10 plus 10 is 20. There's a dot, 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 dot. Right? 10 multiplied by 10 is 100. Or minus 10 multiplied by minus 10 is the same 100. So 10 plus 10 is 20. Minus 10 plus minus 10 is minus 10 minus 10, which is minus 20. So you suddenly find that you're stuck here. And if I'm not mistaken, this was probably one like what my student was trying to do earlier this year, 2023. Just went down the road, A and B and C. I can't remember the question for sure, but I think it's one like this, where she just got stuck. Yeah, because where are we going from here? Right? There's nothing we could do here, you know. Nothing we could do here. So in other words, we have found a case where the AC method doesn't really serve us. We bend the rules a while ago when B and C was equal to 0. We bend the rules when C alone was equal to 0. Notice we bend the rules there. So we're not trying to apply that in normal circumstances at all. We try to bend the rules here and we get stuck. So even in the bending of the rules, very often you go and you go and you go and then you get to a point where you can't go any further. Happens in maths, and as I say all the time, it happens with a lot of other things in life too. A lot of things that you will meet in this maths are things that you will meet in other aspects of your life that mightn't have anything at all to do with maths. But such is the universality of maths. The maths will show up somewhere else, and if you're not aware enough, you would not even recognize it as maths. Right? So we can go further there now. Done. So in this case, the only option we have is the regular option of factorizing a univariate binomial 2 into x squared plus 25. End of conversation. However, if we change plus 50 to minus 50, you see the thing going to get sweeter now. Right? Pay attention. Because 2x squared minus 50, if we were to factorize using the normal method of factorizing a bivariate, not a bivariate, I'm getting confused with binomial and bivariate. Univariate, one variable, binomial, two numbers or two terms or two expressions. No, two terms, because these two terms give you the whole expression when they are connected by the operation of subtraction, right? So univariate, one variable, binomial, two numericals, so to speak. A univariate binomial, right? So with the regular factorization, you get 2 into x squared minus 25. All right, no problem. Let me see how nice the thing going to be now. Here's the real nice part. Here is the real nice part. Stay tuned. So let us apply this to, right? You just make one little change there. You see, instead of being plus 50, is equal to minus 50. Papa, yo mama. Trouble in the camp. Right? So C is equal to minus 50. Yeah, no problem. C is equal to minus 50. So AC is equal to 2 by minus 50. AC is equal to 2 by minus 50, which is equal to minus 100. So now the thing gets sweet. Minus 100, we can start with 1. 1 by, so we ain't have to bring in no 0 here. Because we have an actual value. Right? In the other cases, the AC was equal to 0. So we bend the rules to start with 0, right? But minus 100, 1 by minus 100, we bring in the mirror now, or minus 1 by plus 100. 2 by minus 50 or minus 2 by plus 50. Right? The 3 is not a factor of 100, so that wouldn't work. The 4 is a factor, 4 by 25. 4 by minus 25 minus 4 by 25. We have room for that by 2, 4, 4, 5. Yeah, we have room for that. Alright, so let me write it out. 4 by minus 25 or minus 4 by 25. 5 is also a factor. 5 by minus 20 or minus 5 by 20. 6 is not a factor of 100. We don't use 6. 7 is not a factor of 100, so we don't use 7. Well, minus 100, sorry. Right? 100, same story. We just change the sign. 8 is not a factor of 100, so we dispense with that. 9 is not a factor of 100, so we dispense with that 2. 10 to the 10, 10, 10, 10. 10 shot. So 10 multiplied by minus 10 or minus 10 multiplied by 10. Same value, but we write it twice just to drive home the point. That is plus 10 by minus 10. We flip the signs, we invoke the mirror, minus 10 by plus 10. But for all practical intents and purposes, these two are the same. Now, they may not be the same in theory. So for theoretical considerations, 10 multiplied by minus 10 can be considered to be distinct from minus 10 by plus 10. There are theoretical situations where 10 by minus 10 is not the same as minus 10 by plus 10. But for practical considerations, it's the same thing. So here we do. We could circle this and we could circle this too. Right? No problem. So now we have two pairs of values. Well, we have a pair of values represented in two instances here that are addends of 0, because we can write 2x squared minus 50. We could write that as, let me give the green marker a run out now. Well, let's say we could write that as 2x squared minus or plus 0x. Well, it doesn't matter. So let me say plus 0x minus 50. Right? 2x squared plus 0x minus 50. That is basically what we're working with here when we say 2x squared minus 50, because your b is equal to 0. Right, so how does that enter the picture? Watch carefully. So we have our two pairs of, well, we have our pair of factors, right? One pair of factors will be two factors, right? Now let's see how nice the English is. Right? We have our two factors which are also addends of 0, minus 10 and plus 10. So we could write this over as 2x squared minus 10x plus 10x minus 50, which will give us, when we factorize it now, 2x into x minus 5 plus 10 into x minus 5, which is 2, which will be x plus 5 as the common factor, into 2x plus 10. 2x plus 10 is 2 into x minus 2x, sorry, x minus 5, sorry, is the common factor. X minus 5 into 2x plus 10, right? Which would be x minus 5 into x plus 5 by 2. I just put the 2 on the outside, right? 2x plus 10 is the same thing as x plus 5 multiplied by 2. So this will be x minus 5 into x plus 5 multiplied by 2. Remember, we have 2 into x squared minus 25 here. You'll see the significance of that in a little bit. If we had done it the other way around, we had 2x squared plus 10x minus 10x minus 50, which would be what? Yeah, 2x again. 2x into x plus 5 minus 10 into x plus 5, right? We do the factorization, we put the x plus 5 here. Minus 10 by x is minus 10x, minus 10 by plus 5 is minus 50. So we have x plus 5 as a common factor into 2x minus 10. So x plus 5 into x minus 5 by 2. Right? So following the normal convention in a situation like this, we write the digit first. And we say that this is actually 2 into x minus 5 into x plus 5, which is the same thing here as 2 into x plus 5 into x minus 5. Notice the color scheme I choose. Why I choose blue down here? Because up here we already factorize it in one line as 2 into x squared minus 5. Watch it again before I clear the board. 2x squared minus 50 factorized as a univariate binomial, just like the ones we did in factorization 1, the first video, would give 2 into x squared minus 25. And as a regular factorization, we wouldn't be able to go further than this. However, when we try to impose the AC method on this situation, where b is equal to 0, because you had a negative AC here, you were able to get two factors, a positive multiplied by a negative, that would add to give you 0. Once they had the same magnitude, minus 10 and plus 10, plus 10 and minus 10, you add those two together and you get 0. So we were able to apply that either with the minus 10 first and the plus 10, or the plus 10 first and the minus 10 afterwards. And in both cases, the answer was 2 into x minus 5 plus 5, which we could also write as 2 into x plus 5 minus 5. What's the significance of that? The significance of that is that if you compare this answer with this, or you compare this answer with this, then using basic logic, let me rub off the part in the middle now, because I want to be very clear in terms of what I write in. Right? You have it there, you have it in video, you can rewind as necessary. So we factorize 2x squared minus 50, and we get 2 into x squared minus 25. We factorize 2x squared plus 0x minus 50, which is the same thing, right? Given what we know of 0, right? We factorize 2x squared right? Plus 0x minus 50, right? I put in this in brackets here because we don't really add in anything, right? 2x squared plus 0x. We factorize that using the AC method, and we actually got 2 into x minus 5 into x plus 5. Now, if we agree, and I'm going to write it out, if we are saying if 2x squared minus 50 is equal to 2x squared, right, plus 0x minus 50, and I put in the plus 0x in brackets now, then And watch it now. 2 into x squared minus 25 must be equal to 2 into x minus 5 into x plus 5. Which means, therefore, that x squared minus 25 must be equal to x minus 5 into x plus 5. And what's the significance of all of this? Right? Let me go back, first of all, to the factorization that we did when we were talking about using the AC method here. Remember, we got AC being equal to minus 100. Now, the number 100 is what we refer to as a perfect square. Right? But for us to get two factors that add to give it 0, the AC had to be negative. So your AC had to be minus 100. So you had the plus 2 multiplied by minus 50 to give you a minus 100. As opposed to the previous example before. That's a redundancy, right? Okay, let me just see the previous example. As opposed to the previous example where we had A equal to 2 and C is equal to 50. So 2 by 50 was 100 plus 100. 100 is a perfect square. But in that case where it was a positive value, plus 100, we couldn't get two factors that would add to give you 0. So you have a positive square, so you have a perfect square, but you also have a minus sign. So we get in a sense of difference now with the minus sign. Right? That is significant, because here, we see in here, this is what we refer to as the difference of two squares. And that is what we will be factorizing in the next video. So stay tuned. But let me just wrap up here. X squared minus 25. X squared is a perfect square. 25 is also a perfect square. But only when you have a minus here can you go here. So in other words, if we had x squared plus 25, there is nothing we could do with that. And we saw that in the example before this one. But with the x squared minus 25, based on what the arithmetic is showing us, we can see that x squared minus 25 is actually equal to x minus 5 into x plus 5. And I will do it in reverse just to drive home the point that that is in fact so. So if you had any doubt that x squared minus 25 is x minus 5 into x plus 5, then watch it. Right? Watch the magic here. X minus 5 into x plus 5. Now remember, of course, that this could also be written as, we could also write this as x plus 5 into x minus 5, right? I just reiterating. So don't go off on a tangent, right? Just a matter of personal preference. We already discussed the commutative property. So just choose whatever you're comfortable with and run with it. My personal preference is to do the negative first and then put the positive. But that's just me. You don't have to do it like me. Yeah? So if we have, again, we're doing it backwards just to drive home the point. Right? X minus 5 multiplied by x plus 5. Right? X by x is x squared. X by 5 is 5x. Minus 5 by x is minus 5x. And minus 5 by plus 5 is minus 25. So 5x plus 5x minus 5x is x squared minus 25. And we could choose to do it the other way too, right? I'm going all out because once I record this, the idea is that you, as the person who's trying to learn this thing, should be able to pick it up. You should be able to rewind whenever you want. Right? So if we do the other way around, we say x plus 5 into x minus 5. X by x squared is x squared. x by minus 5 is minus 5x. But x squared first, minus 5x, right? Plus 5 by x is plus 5x, and plus 5 by minus 5 is minus 25. That is the same, x squared minus 25, because minus 5x plus 5x is 0. So if you had any doubts at all, x minus 5 into x plus 5 is x squared minus 25. X plus 5 and x minus 5 is the same, x squared minus 25. Right? But this happens only when you have two perfect squares. You have a perfect square here, and you have another perfect square here. And you have a difference between them. All of this wouldn't work for addition. Right? So this is what we refer to as the difference of two squares. And that is the next set of factorization that we'll be doing. That will be factorization 5. So stay tuned.